Okay, for this next segment, I want to talk about how to balance chemical reactions, which can get kind of sticky, as well as the law of conservation of mass, and that's the reason why we have to balance chemical reactions. And so those are the things I want to talk about here, and then we'll start practicing some of that stuff. So for balancing, we have to acknowledge that there are some molecules that are diatomic. And here's that prefix. Remember, the prefix di means two. And these are elements that are found in nature in pairs. So there are certain elements out in nature. When they're found, they're never found as a single atom. They're always found paired up with an identical copy. So for example, when you look down there, hydrogen, hydrogen's diatomic. And so hydrogen is always found with a partner hydrogen. Hydrogen is never found by itself. So when these elements are found by themselves and are not bonded with other elements, they're always found in pairs. And there are only 7 of them. Out of the 120 elements that we know of, there's only 7 of them, and we just have to memorize them. And here they are: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And then you notice, since they are found in pairs, each one of them has a 2. So because they're diatomic and they're by themselves, they have to have the 2. In terms of knowing them, we just have to kind of memorize them. They're not that easy to memorize. I'll show you a couple things you can do. I like to use this. I'm going to if I rearrange the letters: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. It kind of sounds like Brinkelhoff, kind of a nonsense word, but it helps me remember them, and that's the one that I like to use. So as we go through these diatomic molecules, you'll hear me refer to the Brinkelhoff. Another way you can do it, if I go over to the periodic table and I highlight them, here they are right here actually: nitrogen, oxygen, fluorine, and then chlorine, bromine, and iodine. There we are. That kind of looks like the number 7, but we can't forget hydrogen over here. Hydrogen's off all by itself. So there are the 7 diatomic molecules. Either looks like the number 7, you just can't forget the hydrogen off by itself, or it kind of looks like a hockey stick and a puck. However you want to view that, whatever's easiest for you to remember. So the number 7, hockey stick and a puck. My preference is for the Brinkelhoff, and that's what you will hear me talk about. Showing some of these, though, if I go back to the types of reactions and some that we showed, if we go back earlier in our notes, this 2, for example, right here, oxygen is part of the Brinkelhoff, meaning when oxygen's alone, it's diatomic. It has to have a 2. If you notice lithium has a 1. Lithium is not part of the Brinkelhoff. Doesn't have it. It's just found it's all by itself. When we come over here, notice how the numbers change. Remember that, you guys. We've been here, though. I'm going to try to erase. And I'm going to try that one more time. And so here now, we know this. These numbers are here because of the crisscrossing. So once the elements come together to crisscross, or once they come together, we have to crisscross. For the diatomics, we're only talking about elements by themselves. Here again, hydrogen, all by itself, it's part of the Brinkelhoff. Oxygen, all by itself, it's part of the Brinkelhoff. Here, this is a compound. This doesn't count. That doesn't count for the Brinkelhoff. This is a compound. Doesn't count. Sodium, not part of the Brinkelhoff. It has a 1. Chlorine is part of the Brinkelhoff. That's why it has the 2. So we have to start recognizing these and putting those 2s in whenever it's necessary. Saw that one already. Here, compound. Doesn't count. Hydrogen is all by itself, so it's got to have a 2. It's part of the Brinkelhoff. Copper is not part of the Brinkelhoff. And the last part's a compound. Doesn't count. Diatomics don't count on the compounds. Zinc is not part of the Brinkelhoff. That's a compound, so it doesn't matter. Remember, we have to do the crisscross. That's why that 2 is there. It's just a coincidence. And hydrogen's by itself, so that's why we see that 2 there. And last one, if you take a look at these are all compounds. No diatomics when it comes to compounds, remember. So those are the diatomics. And again, I like to use that Brinkelhoff, Brinclhof. That helps me remember the 7 diatomic molecules. And so now we take this to balancing chemical equations. And so we go to the law of conservation of mass, and that means we can't create mass and we can't destroy mass. So if we start with 10 grams of reactants, we have to end with 10 grams of products. Meaning if we start with 10 grams in the reactants, we can't magically end with 8 grams in the products, or start with 10 grams and somehow end with 12 grams. Whatever we start with, we end with. It's kind of like a deck of cards. There's 52 cards in the deck. Shuffle them up, deal them out. There's still 52 cards in the deck. There's not more, there's not less. There's always 52 cards in the deck. And so here, the idea, we're going to do this. If we start with 4 oxygen atoms, we better end with 4 oxygen atoms. I compare that to when you're babysitting. Those of you that babysit, if you start babysitting 4 kids at the end of at the start of the night, you better have 4 kids at the end of the night. If mom and dad come home and there's only 3 kids, you're in trouble. Or if mom and dad come home and all of a sudden there's 6 kids, you're in trouble. If you start with 4, you better end with 4. And so we're going to use coefficients for this, and we use those in math class. And so that's one thing we'll copy from math, which is really nice, coefficients. Coefficients are the number out in front. In math class, if I have something like this, 2x, that 2 out in front, that 2 is a coefficient. And so that's what we call that. That's what we use it as, and we're going to use it the same way here in science. And so when I put a 2 out front, that means I need 2 water molecules are needed. Well, here's H2O. But if we have 2 of them, that means I have 2 oxygen and 4 hydrogen because I have 2 molecules. And so we're going to start doing a little bit of math. Luckily, it's really simple math, but we are going to do a little bit of math. So an example of balancing a chemical equation, here's the equation in words. Aluminum plus oxygen yields aluminum oxide. So we want to balance this. I want to start and end with the exact same amount on both sides. So aluminum, not diatomic, so that deserves a 1. Oxygen is diatomic, so it's got a 2. And then notice here, we do our crisscross. And so now notice, I start with 1 aluminum, and I ended with 2. I started with 2 oxygen, and I ended with 3. So this would be where we're saying, this is not balanced. We have to get this balanced. We have to be able to show that we start with the same amount of aluminum, end with the same amount, start with the same amount of oxygen, and end with the same amount. So here's where the math comes in, and coefficients. This one's going to be confusing, but we will do some examples, don't worry. So if I put a coefficient of a 4 out front of the aluminum, here's my math. I take the coefficient times the subscript, and that gives me 4 aluminum. I put a 3 as a coefficient out in front of the oxygen. I take the coefficient times the subscript, and that gives me 6 oxygen. And then I go over here to my products. Remember these terms. I go over to my products. I put a 2 out in front. That means I need 2 aluminum oxides. Well, 2, I take the coefficient times the subscript, gives me 4 aluminum. I take the coefficient times the subscript, 2 times 3 is 6. And now as I look at this, I started with 4 aluminum, ended with 4. I started with 6 oxygen, and I ended with 6. This now shows conservation of mass. We started and ended with the same amounts.